Welcome to the online training, Intel Hyperflex FPGA Architecture Design, Analyzing Critical Chains. My name is Marlon Price, and I will be the presenter for this training. During the presentation, you may pause, stop, and start the training at any time. On the left side of the window, you will find the Menu tab, which allows you to skip forwards or backwards to specific slides. There you will also find the Notes tab, so you can follow along by reading a script of the course. During this training, we will start with an introduction to the critical chain, in which you will learn what is meant by the term critical chain with regards to the Stratix 10 Hyperflex architecture. In the next section, Analyzing Critical Chains, you will learn how to read critical chain reports generated by the Hyper Retimer to interpret their structure. And finally, by the end of the last section, Critical Chain Types, you will know the 4 types of critical chains and be able to fix them so as to improve your Hyper Retimer results. So first, Introduction to Critical Chains. Traditional FPGA architectures today have the concept of the critical path. A critical path is the slowest path between any 2 registers within a clock domain. Since the clock cannot reliably run any faster than what is supported by the logic delay between these 2 registers, the critical path between the registers effectively defines the maximum clock domain speed, or Fmax. Timing closure, then, involves iteratively making critical paths faster until you reach the target clock speed required by your design. Thus, timing closure is a local problem, meaning you are always focused on fixing the critical path or a few critical paths. In the first diagram on this page, the critical path is between registers X and Y. So timing closure efforts will be focused on the path between X and Y. While some timing closure strategies may look beyond X and Y to registers W and Z and no further, the main focus would be between X and Y. With the Hyperflex architecture, timing closure becomes more of a global problem. This is because the Hyper Retimer is responsible for normalizing the logic delay across multiple register stages by moving register backward and forward along timing paths. So the path between 2 specific registers is no longer the limitation. The limitation is based on how well can the Hyper Retimer spread the registers out along a path to reduce the average delay between any 2 registers in the clock domain. So in the second example on this slide, you have A, 4 registers in series, and then B. The absolute best performance for this path will be the total delay between A and B divided by the number of register stages between them. So while the individual delay between any 2 registers will define the actual clock speed, how close you can get to the absolute best performance is defined by how well the Hyper Retimer can spread all the registers between A and B out, getting them to their ideal locations. The critical chain, in the context of retiming, is the single design path for which the Hyper Retimer can do no further optimization. In other words, the Hyper Retimer has spread out the registers along the path as much as it possibly can, but it cannot make the timing any better. So the path for which the Hyper Retimer fails to achieve a target clock speed is reported back as the critical chain. Note, the critical chain may be the result of an individual path, or it can be the result of an interaction between multiple paths. You can think of the critical chain as a critical path abstracted to a higher level. While the critical path resolves itself to a specific register-to-register delay, the critical chain can involve multiple register-to-register delays along a timing path. To understand the critical chain better, we can use the diagram on this slide. Here, register A cannot move any more to the right due to some restraint or restriction. Register B is likewise also prevented from moving to the left. Sometimes registers A and B are actually the same register, meaning you have a loop. In any case, the Hyper Retimer distributes the registers in between A and B as much as it can to reduce the average delay, but it cannot make this chain of registers run any faster. If the clock domain performance is determined by two registers in the path between A and B, then the path between A and B becomes the critical chain. Next, we look at analyzing critical chains and the critical chain report. The critical chain is only provided by the tools where the Hyper Retimer is prevented from optimizing the design any further. It happens during the compilation retime stage when the retiming registers is not able to produce any additional performance gain to the clock domain. It happens during fast-forward analysis when fast-forward modifications fail to produce any more speed increase to the clock domain or at the fast-forward limit stage. As a result, understanding and fixing critical chains is key to reaching the fastest clock speeds for your designs, speeds beyond those possible with the current RTL. The screen capture on this slide shows a diagram of a fast-forward report. As you can see, the fast-forward limit step or stage is being selected. As a result, in the tabs below, you can see the critical chain details report and the recommendations for critical chains report. The Critical Chain Details tab provides a timing analyzer-like description of the path or paths that make up the critical chain. Use this as a starting point in understanding the structure of the critical chain that is limiting performance. Keep in mind that only the most critical chain is being reported. With the complexity of retiming dependencies that can exist in many FPGA designs, the chance is very high that there are multiple paths structurally similar and related to this one. So fixing the chain will commonly involve taking a wider view and fixing the overall structure creating the critical chain. But you can use the critical chain path here as a starting point for identifying that structure. The Recommendations for Critical Chain tab provides very helpful tips on what can be done to the critical chain to reduce or remove its impact on performance. Use this tab as a starting point for understanding why this particular critical chain and the structure it is contained within has appeared in the report. Any solution to the critical chain should really begin with looking at the recommendations on this tab. Here is an example screen capture of a critical chain details report. Some critical chains are made up of a single path. Many critical chains, like this one, are made up of path segments. It is the interaction of the path segments either directly or through retiming dependencies that cause the critical chain to occur. From what we see here, this critical chain is made up of at least two path segments. The path info column of the report explains why the particular path segment or subset of the path segment is a part of the critical chain. In other words, what is the path segment doing to cause or aid in causing the critical chain? This critical chain, for example, is made up of the interaction between a long path segment and a short path segment. The basic types of path segments found in the path info column of the Critical Chain Details report are long path critical, long path, short path, extend to locatable node, and retiming dependency. A long path critical indicates the segment or a portion of a segment that is the true critical path. In other words, the path that the Hyper Retimer is trying to improve through retiming but can't. View all other path segments in light of how they are preventing this critical portion from retiming as the retimer would like. A long path indicates another segment with available locations for retiming. It is not the critical segment or portion of the segment, but it is interacting with the critical portion or segment in some way. A short path indicates a path segment that has empty hyperregister locations in it, but those locations cannot be used due to their proximity to registers already placed and the hold time violations that would occur if they were enabled. As a result, this short path is preventing retiming on a longer, more critical path. Extend to locatable node indicates that the endpoint of the path segment has been extended beyond the actual path endpoint to end at a register. By forcing all path segments to end at registers, then they can be understood and viewed more easily in other path viewing tools found in the Intel Quartus Prime Pro software. When retiming dependency appears in the path info column for a critical chain path segment, it means a retiming dependency or relationship exists between the specified register IDs. The effect of the retiming dependency is that what happens to one, moving a register through the register ID for example, effectively has to happen to the other register ID. So the 2 points are joined together from a retiming perspective. So in some respects, you can treat them as a single point when it comes to their relationships with other register IDs. Looking at the example on this slide, the retiming dependency from the sample critical chain report exists on the path between register IDs 5 and 4. Thus, retiming into number 5 means retiming into number 4 as well, and the opposite. If we look at the rest of this critical chain path segments, we would find all of the points that make up this retiming dependency path segment, including register IDs 5 and 4, also exist as part of other path segments. So this retiming dependency effectively locks those other path segments together from a retiming perspective, even if the segments do not intersect directly within the critical chain. Again, due to the dependency, retiming one segment means you have to retime the other. A trick you can employ with retiming dependency path info segments is to combine the register ID names together. So you could call the retiming dependency in this example register ID numbers 4 or 5. This helps especially when it comes to loop evaluation, as you will see later. Going back to the critical chain details report, the register column describes the state of the registers that make up the chain. In this column, reg means a used ALM register or hyperregister in the path. Bypassed hyperregister means a usable empty hyperregister location in the path not enabled by the hyper retimer, meaning the hyper retimer could have used this register if it needed to. Bypassed ALM register means an ALM register enabled by the fitter but bypassed by the hyper retimer for better performance. Unusable hold means an empty hyperregister location that could not be enabled due to a hold proximity restriction with another enabled register or hyperregister. These definitions help in describing the critical chain to you so you can understand why it is a critical chain, located in your design logic, and, using the recommendations for critical chain, you can figure out how to potentially modify your RTL or design constraints to get past this chain. The register ID column assigns a unique number to each register in the chain. This helps more easily identify the chain registers, particularly when the registers are shared by multiple path segments. And finally, the element column provides the name of the resource object or design node. Again, use the details report to understand how this design structure caused the limiting reason reported by the tools. If you try to retime the registers in the long path critical segment, what effects do the rest of the segments have on preventing that retiming? When trying to work around the performance limitation of your critical chain, you should always first check out the information provided in the Recommendations for Critical Chain report or tab. Here, the Hyper Retimer tries to point you to those locations in your critical chain where retiming cannot be performed and provides the reason why retiming cannot be performed there. It then provides suggestions on what you can do at those points to eliminate the critical chain. So if anything, these recommendations can help you understand why the critical chain occurred. But even better, these recommendations will help you understand where new registers can potentially be added that would help you increase your clock Fmax. Here in this example screen capture, we can see there are retiming restrictions occurring at 2 points in the critical chain where clock crossings are occurring, at registers OQ-Reg0 and OQ-Reg56. Thus, a potential solution is to add more registers at these points if the design allows. For additional help in understanding the critical chain, you can cross-probe the chain into the fast-forward viewer window to view a graphical representation. Just right-click on any row of the critical chain and select Locate Critical Chain in Fast Forward Viewer. Keep in mind that your design has gone through synthesis, fitting, and retiming optimizations, so the display may look very different from your RTL. With Fast Forward Compile enabled, the Hyper Retimer modifies the netlist on its own. So instead of stopping and reporting a critical chain, Fast Forward Compile automatically edits the critical chain and continues on to the next. To do this, it employs Hyper Retiming to remove barriers to retiming like asynchronous clears and use and preserve attributes, Hyper Pipelining to add new registers to the critical chain path, and Hyper Optimization to do some advanced design changes beyond Hyper Retiming and Hyper Optimization. Fast Forward Compile then reports back to the user the netlist changes that were made to improve performance so the designer can implement the solutions directly in their RTL. No more trying to iteratively understand and fix critical chains. Fast Forward Compile only quits and reports a critical chain when it cannot improve the design performance through its design modifications. But at that point, the designer already has a path to achieving a target clock speed. The designer is only concerned with the critical chain if he or she wants to achieve target clock speeds beyond those reported by the fast forward at limit step. For our last section, we will look at different types of critical chains and some potential solutions for fixing them. There are 4 critical chain types reported by the tools: insufficient registers, path limit, short path, long path, and loop. Each of these refers to a specific condition at which the Hyper Retimer or fast forward cannot improve performance. Thus, any one of these may appear as the critical chain during Hyper Retiming or during fast forward analysis. Regardless, the tools will always report recommendations on how to fix any of the critical chain types that occur, and you can use those recommendations as a starting point for your own solutions. Be aware, though, that some critical chains will be harder to fix than others, depending on the structure of logic causing the chain and how it is described in your RTL. The first and simplest critical chain type is insufficient registers. This critical chain occurs when a path simply does not have enough registers in it for the Hyper Retimer to improve timing. As shown in this example, the path here has 2 registers in it. The Hyper Retimer has spread the 2 registers as far apart as it can and as far as it can from the endpoint registers not shown in order to reduce the average delay between all of the registers, but the path cannot be improved upon any further. So the critical chain is reported back as the 2 endpoint nodes, the registers who cannot be moved at all, and all of the logic and registers in the path between them. In most cases, the critical chain can be fixed with either Hyper Retiming, removing register restrictions, or Hyper Pipelining, adding more registers. This can be done automatically during fast forward analysis. In that case, you simply have to repeat what fast forward has done. But sometimes, depending on the complexity of the logic, this chain type may appear at the fast forward limit, which may require structural changes to your design or code. This is an example showing how hyperpipelining fixes an insufficient register critical chain. Here, 2 additional registers have been added to the path. Where they are added does not matter, but in this case they are added to the input side of the path. Once added, the Hyper Retimer will then redistribute the registers to ideal locations so as to reduce average delay and improve overall path performance. Here is an example critical chain. In this case, we have 3 path segments, 1 long path, 1 retiming dependency, and 1 log path critical. The long path critical segment is the path segment the Hyper Retimer is trying to fix. Notice that register number 5 at the bottom says required. That means that this register cannot move. So the only solution is to retime 4 forwards. That seems simple enough, but number 4 has a retiming dependency to number 3 as is indicated by the middle path segment. This means if we want to move number 4 towards number 5, we also have to move an equivalent register towards number 3. To do this, the long path segment from number 1 to number 3 must also provide a register to read time along with number 4, in this case register number 2. Well, what is wrong with that? The problem is the Hyper Retimer is in a no-win situation here, as there is an opposing relationship between the two paths. In other words, if we retime number 4 and number 2 forwards, while that makes the timing of the path from number 4 to number 5 better as they get closer, it makes the timing of the path from number 1 to number 3 worse as number 2 moves further away from number 1. So there are not enough registers in the chain to improve both paths. If we use hyperpipelining to add more registers, then all paths can retime forwards, in this case for performance gain. The second type of critical chain is the path limit critical chain. With this critical chain, the hyper retimer and/or fast forward cannot make the clock domain any faster because there's simply no more hyperregister locations in the path that will result in performance improvement. So unlike insufficient register critical chain, where there are empty hyperregister locations but not enough registers in the design to make use of them, the path limit critical chain is kind of the opposite. In this case, there are enough registers but nowhere to actually move them based on the current layout of the design. In some cases, this is not a bad critical chain to see, as it may occur after the performance limit of the silicon has already been surpassed, meaning the design and the device can't go any faster. So there is nothing more for you to do anyways. In still other cases, the path limit critical chain may be due to DSP and RAM block registers not being enabled. This is because the hyper retimer cannot modify the structure of DSP and RAM blocks. So if their registers are not enabled by the design itself, then there is nothing else the hyper retimer can do to them. So it will report the path through the DSP or RAM block as a path limit critical chain. Fast forward analysis will turn these registers on just to show you the performance gain that is possible if you modify your design to enable them. The third type of critical chain is the short path, long path critical chain. This type of critical chain occurs at the intersection of two diverging or converging paths in which one of the paths is a short path and the other path is a long path. The long path, being longer, has more logic and routing in it. This means that it has many hyperregister locations in it for use that the hyper retimer wants to retime into to reduce the average register-to-register delay through it. The short path, being shorter, is a more direct connection and as a result has fewer hyperregister locations in it. But since the two paths are connected, in order to retime into the longer path, the hyper retimer has to likewise retime into the shorter path. In retiming into the shorter path, the hyper retimer runs into hold time issues because the hyperregister locations that are unused are too close together. So, in not being able to retime into the shorter path, the hyper retimer cannot retime into the longer path either. Since the hyper retimer cannot change the layout of the design, it is stuck and the two or more intersecting paths are reported as a short path, long path critical chain. This slide shows an example of a short path, long path situation. In this case, we are taking a value and comparing it against the result of that value after it has been processed in some way. First, we have the long computation path. This path the hyper retimer wants to improve by retiming registers into the unused hyperregister locations along it. Then we have the corresponding short path. Since this path contains the unprocessed value, the fitter routes it directly to the comparator, so there are very few hyperregister locations within it. So if the hyper retimer wants to retime into the long path, it must also retime into the short path. But to do so, it would have to retime into a hyperregister location that is too close to the register on the right, so that is an illegal move for the hyper retimer. So in effect, there is nothing the hyper retimer can do. This slide shows an example of a short path, long path critical chain. In the report on the right, you can see that the long path critical segment between registers 1 and number 2. Again, this is the path the retimer wants to fix. Notice the other path segment is a short path with the same endpoints. So moving number 1 forward would require moving number 1 into the short path. and moving number 2 backwards would also require moving number 2 into the short path. But in the short path, the empty hyperregisters there are classified as unusable due to hold. This means that the empty register locations are too close to number 1 and number 2, and thus neither endpoint can move any closer, effectively blocking the registers in the long critical path from moving as well. One potential fix for short path long path is to duplicate the registers. By making a copy of register number 1, then the long path and short path are separated. Thus, the retiming can handle the two paths independently by retiming the longer path without having to retime the shorter path. When using this method, it is recommended that you use the synthesis attribute "don't touch" on the duplicated registers to prevent synthesis from optimizing the duplicated logic away. Make sure not to use the preserve attribute, as that prevents retiming. In many cases, the short path long path situations are automatically solved by the fitter by adding extra rounding to the short path. But if short path long path critical chains do appear, a designer can use techniques such as hyperpipelining and node duplication to solve them. The fourth and final type of critical chain is the loop critical chain. The loop, of course, being a feedback path that returns to a prior point in the design. The Hyper Retimer can retime registers around a loop. As you can see in the follow-up hyper-optimization training on loops, the Hyper Retimer can also retime registers over the loop to the other side. But the Hyper Retimer cannot add or remove registers to the loop, as it would change the functionality of the design. While a feedback path back to a prior location is an easy loop to see, another type of loop can be sort of tricky. This loop involves retiming dependencies. In this case, the looping path does not return to the same point, but to a path that has a retiming dependency to the prior point. Recall from earlier in this presentation, when retiming dependency nodes were introduced, it was said that the nodes with a retiming dependency relationship between them can be treated as if they were the same point. That is because retiming dependency made it so that what you do to one node, you effectively have to do to the other. So what happens with loops created by retiming dependency nodes is that the loop path does not return to a prior loop point, but instead the loop path leads to a node that has a retiming dependency with the original node. So from a retiming standpoint, a loop still exists. In this example here, register IDs number 1 and number 2 have a retiming dependency. Thus, retiming into data A, register ID number 1, requires retiming into data F, register ID number 2. Since there is also a path that leads from data A to data F, or register IDs number 1 to number 2, these conditions form a loop in the eyes of the Hyper Retimer. Here is an example of the simplest of loop critical chains. It is called an RTL loop, which means that the loop is actually defined in the code itself. A diagram is included on the left to help visualize it. Looking at the critical chain details report, even if you do not understand the chain or the path it is describing, you can see that the critical chain starts at register ID number 1, passes through a series of logic structures and interconnects with available hyperregisters, and returns back to register ID number 1. In this case, it's the RX fill reg register. The loop critical chain on this slide is an example of one that is slightly more complicated. It is a retiming dependency loop, which means the loop is not directly created by the RTL code, but is created through retiming dependencies. Again, we include a diagram on the left to help visualize. Looking at the critical chain details, we can see a long path that proceeds from register ID number 1 through some logic including register ID number 2 and an adder chain, and then arrives at register ID number 3. Another segment of the chain is a shorter path that goes from register ID number 4 and back to number 1. It is still a long path, as there is an unused and available hyperregister on it for retiming if needed. But how is this a loop? The loop is completed by the middle segment, the retiming dependency between register IDs number 2 and number 3. Assuming register IDs number 2 and number 3 are the same point, you have a path from number 1 to number 2, 3, and from number 2, 3 back to number 1. Anything you do to the critical portion of the path will require pulling a register from the other end of that long path through the retiming dependency. Like the last slide, the important thing with the critical chain is to figure out where the structure is in your RTL so you can go modify it. If looking at it from a high level, for example, see the module. Many times loops are caused by data buses that feed back and pass through processing like addition, multiplication, and shifting. When this happens, a single bit of the bus does not necessarily feed back and connect to a point that is the same bit of the bus, but another bit of the same bus. This can show up as a critical chain loop. A trick to detecting this situation is, when looking at the critical chain details, replace the bit value in the chain with an asterisk. Then you can tell that the bus loop is returning to the same location, but just a different bit of the bus. So if you find you have a loop critical chain and you want to run the design faster than that loop critical chain allows, there are 3 basic ways to fix it. 1. You can recode your RTL to completely remove the loop, changing the feedback structure into a feed-forward structure. 2. You can reduce the size of the loop by removing computations being performed within the loop path and implementing them instead in the forward path locations where they can be pipelined. Or 3, you can manually insert new registers into the loop path to reduce the average delay between the loop registers and thus allow the loop to run faster. Once this is done, you can compensate for the additional registers in the loop by modifying the surrounding non-loop logic. All of these techniques will be covered in follow-up online training under the topic of hyperoptimization. This concludes the online training, Intel Hyperflex FPGA Architecture Design, Analyzing Critical Chains. In summary, from this material, you can see that critical chains are an important aspect of Intel Hyperflex architecture performance analysis, as they are the key to understanding your performance limitations with respect to retiming. So by modifying your design to fix your critical chains, you can get your design's clock rate to speeds higher than what is supported by the current design structure or RTL. If you want to learn more details on understanding and modifying critical chains, please see the Stratix 10 High Performance Design Handbook found on Altera.com. If you would like to continue in your learning on the Stratix 10 design flow, we recommend the follow-up training, Introduction to Hyperoptimization. In this training, you will learn what makes up hyperoptimization and how you can use fast forward as the starting point for your hyperoptimization steps. Intel FPGA provides many self-help resources when you need design assistance. For example, there are web pages called landing pages dedicated to specific FPGA technology like transceivers, DSP, OpenCL, and high-speed gigabit interfaces. There is a community forum, and there are hundreds of training courses available just like this one. This concludes the online training, Understanding Critical Chains. This concludes this online training. Again, my name is Marlon Price, and I thank you for your time.